My talk is going to be an extension of Siddharth's talk, essentially. But I'm going to talk mostly in anti-de Sitter space. I'll explain as we go along. This is a work in progress with Kyriakos, Olga, and Subrat. And Pushkar will also talk some more stuff about this tomorrow. So firstly, I'll define the question, and then I'll explain some ideas which are sort of key to our analysis. And part 3 will be kind of like the major chunk of what I'm interested in. Finally, I'll leave with some comments on black holes and conclusions. Okay, so the first question is something which Siddharth already mentioned previously, and it's about trying to determine if we can completely understand an excitation which is created in the bulk by only using boundary correlation functions. That is we have some state defined inside, and we want to measure what that state is by only doing measurements outside. And if we can do that, the next question is, can we measure all possible states? Or what are the classes of states we can actually perform a measurement in, and how complicated are these measurements? And finally, all of this is really leading to this question where, if there is a black hole with an excitation inside or without an excitation inside, can we actually distinguish between these two things? Most of these questions are motivated from the fact that we cannot really do, we cannot do much in classical mechanics for all of these three, and I'll try to explain this more later. Okay, so firstly, I'll just review something which all of us know, which is the Gauss law in electrodynamics, and that just states that if I have a charge somewhere inside, and the thing which I can actually really measure is that the electric field somewhere outside, and if I can measure something like this, a surface integral of E over small elements, then I can actually recover an information about the whole charge which is present inside. Now I can also do this in order to measure the total charge inside, and this is what we generally do in classical electrodynamics. That is, let's just say we had a charge Q1 and Q2, then the total information that I would get by measuring surface integral of E dot ds is really Q1 plus Q2. And the question is, can we really distinguish this state from this state, where I no longer have a Q1 and Q2 present, but I have Q1 minus alpha and Q2 plus alpha, such that the summation is remaining constant. Of course, one thing that people can suggest is that you can immediately think of something like a dipole moment, and you can consider quadrupole moment and so on and so forth, and that's true that they might give us more information, but suppose if I consider them to be spherically symmetric shells, then really I would not get anything more than Q1 plus Q2 in general. And that's true that we can in general just get Q total, and there exists a similar statement in gravity, where you no longer think about in terms of electric charges, but you think about think of it in terms of the total energy being present inside. And all of these seem to suggest that they come from measurements of the form the total charge or the total Hamiltonian. And in everything I talk about, all these operators are going to be living on the boundary of any system I have. So if I talk about ADS space, then it's going to be on the boundary of ADS space. And like I said, you can also study various other things like the dipole moment or the angular momentum and so on and so forth. Okay, now comes the important part, that suppose we are allowed to measure more than this, and this is where the distinction between a classical and a quantum measurement actually comes into picture. If I want to think about operators like this, where O can be just any function of the field I'm considering. Let's say I'm just considering a scalar field and I want to measure that, then I can think of measuring things like HO or HO1, O2, where all these O1, O2s, and O's are insertions on the boundary. And if I was just in the regime of classical physics, then all of these would reduce to products of expectation values, not really revealing anything more. So hence, I want to think of these as quantum correlation functions, and this will become a little more clear in the next slide. But one thing which I have to specify before that is, what do I mean by these expectation values? And these expectation values generally done on some state psi, where the state psi is defined by acting with some unitary operator on the vacuum. And we can define the vacuum in various ways in ADS. And this thing is also going to become a little more clear in the next slide. Okay, so the first thing is I would want some properties that the Hamiltonian satisfies. And one property that I wanted to satisfy is that it generates time evolution for me. I can have a similar property for a charge operator where it gives me the charge of the field. And another thing is that it annihilates the vacuum. This O, like I said, it can be just thought of as some scalar field. Okay. The next thing is about the meaning of a state, like I said. So here I want most of my states to be generated by some unitary operator. Now you could consider classes of superpositions, but they would have some overlap with standard QFT, which I don't want to immediately go into. But the main idea is this. I'm going to define a state like this, with lambda being some parameter in which I'm going to do a perturbative expansion on. And phi of f is just defined as this integral, which comprises of the scalar field phi and some smearing function f. This f is really going to allow me to localize the state in some certain region. And the main goal of us is to try and recover this function f by making some sort of boundary measurements, by considering correlators of these kinds. And in this entire talk, I'm only going to be speaking about this correlator. However, one can talk of some things more. So just to make it a little bit more precise, like I said, okay, so this is a rough picture of what ADS space is. The only thing, one reason why you want to consider ADS is because it's almost naturally like a box. And other than that, you don't have to deal with some other charges like supercharges, etc., which Siddharth was talking about. But the goal is this, that you create some disturbance here in the bulk, and these areas on the right are on space-like separation with the area at the center, which means that you can perform measurements independently on the center versus these, and they're just space-like separated. And so the non-trivial part would be, in order to recover this, by only making measurements here at the boundaries and in those regions. And one thing that will be important to me is that I'm not just in one particular time slice, but I'm allowed to go into a slight width, which I'll be calling epsilon. That is, I'll be working in a small time band. And this thing will be slightly essential in the next slide. Okay, so one thing is, and this is kind of the main point, is that if we, like I said, we'll be measuring things like H and O, and where the time band epsilon is here. And this can be expressed in terms of this function f, which I want to recover, times something called the bulk to boundary propagator, which just appears from standard quantum field theory, where you just have two scalar fields separated between two regions. And the goal is to recover f in this thing. One important thing is that I'm still working at first order of lambda, where lambda was defined in the definition of a state. I said I'll be using a parameter lambda in order to make perturbative measurements. And this function f, you could try and think of recovering this in various different ways. One simple idea that one might think of is to multiply with some orthogonal function, but that doesn't seem very easy to do. So one idea is that you can work in series of epsilon, and you can try and get all moments of f, essentially. On the right-hand side, if you're allowed to go into, you can expand to as much order of epsilon you like, and you can, in principle, get all moments of f, and this is some function whose all orders of epsilon are known to you, so you can, in principle, recover f. However, if you had, like I said, if you had more complicated states, which could be of the form this or something like this and so on, then you would need to make more complicated measurements. Such a simple measurement would not allow you to just get back the function f. Okay, so these are like two main important points. Let's suppose we just have two simple wave functions. By two simple wave functions, I mean wave functions which are just of the form e power I phi f, which have different bulk values, but are overlapping in the boundary. This is some case which would not be allowed, because in principle, if they give the same values in the if they give the same values in the boundary, we should be able to get the same function inside. And in other words, if they're differing in the bulk, they must have different traces on the boundary. Okay, so this is mostly the thing I was talking about in empty ADS, that is just ADS without any excitation. And this is something which Pushkal will be talking in tomorrow. This is just a rough picture of a black hole in ADS, where this dashed line denotes the horizon of the black hole. And this thing in here would just be a free black hole, that is a black hole without any excitations inside. And this thing in here would be a black hole with some excitation inside. And we can try and repeat the same procedure that was described before in order to recover something like this. And this would have some more implications for the information paradox that Pushkal will demonstrate tomorrow. You can also try and think of repeating something like this by just considering some charges in electrodynamics. You can in principle think of recovering you can think of making a measurement on the outside of some box, trying to understand what kind of charge is present inside. And with that, I'll conclude. Okay, the first thing is that we can recover a state inside the bulk by making measurements on the boundary. And all of this is actually done without making any reference to string theory. Although a large part of this is expected from string theory by a principle called holography or ADS CFT. But where they actually talk about measurements of correlation functions on the boundary by, and basically relating correlators in ADS to correlators in CFT. But here we are not bringing any of that into picture. We are just talking about how quantum theory of gravity in principle can have all of these. Although a few of these things which I talked about would also follow into electromagnetism, but I think Siddharth also mentioned this, but in electromagnetism we can have gauge invariant operators, something like F squared or something, which would mix up two states and we cannot exactly recover this. And yeah, this is the last slide, that we could recover states behind the horizon. And this may serve as a protocol for bulk reconstruction, but this is still work under progress. And there might be some things in 3 dimensions also which might be of special interest because of some more dualities. Yeah, these are some references, and I'm done. Thank you. Yeah.
Thank you, Chandramouli, for this talk. If there are any questions.
Thanks, nice talk. What is an easy way to see what is an excitation inside a black hole?
What's an easy way to see? Well, you would be making measurements of similar kinds. Okay, so for example, this particular slide here shows you how we can get a toy model of a horizon. You know, that you can really just think of this as a toy model of a horizon where you're having some state here which is completely space-like separation. So this thing mimics a horizon of a black hole, but of course the horizon of a black hole has more properties, which we don't really need in this case. But if you're asking for some experimental measurement,
No, not for experiment. I'm just trying to understand what it means to have an excitation inside a black hole. I don't understand that physically.
Oh, you could. Well, I could always create some sort of a state like this on top of a black hole microstate, and that's what I mean.
Maybe I'll talk to you later.
Sure.
So I didn't understand in what sense it's a boundary measurement. Like you have this correlator. I mean, is the observable kind of localized at the boundary, or?
Yes. So this O lives on the boundary.
The O lives on the boundary.
And H is also an operator naturally present on the boundary.
H is not the Hamiltonian of this entire system.
Right. H is the Hamiltonian of the whole system. But what happens in gravity is that the bulk Hamiltonian, the Hamiltonian present inside, is actually set to 0 by the constraints in the theory. The theory is so constrained that the bulk Hamiltonian naturally becomes 0. So the Hamiltonian is just defined as a surface integral over the boundary.
Yeah. So is it correct to say that this is for a semi-classical, it's true in a semi-classical expansion, meaning that it's true for small perturbations about a background, if you're looking at quantum fluctuations around the background. If you were to consider superpositions of backgrounds, then it would be more difficult.
Superpositions are more difficult, and we're trying to explore what happens, I think. So superpositions are more difficult, yeah. As of now, this thing just works. As of now, I'm only interested in states which behave like this, where, you know, let's say this is the background and you're just doing it this way. I don't want to add a black hole on top of this state immediately, but yeah, I think we could do that as well, but we are still exploring that.
Thank you again, Chandramouli. We would like to thank him with a round of applause.